দাঁড়াও।
Hello, check, check, check 1 2. Hello, hello, check, check, check 1 2. ঠিক আছে বাবিদা?
Generally, I mean, other than emergency department, but in ওটা সুবিধা ফলতে বলেছিল যে তাড়াতাড়ি দেরি করে আসি তাড়াতাড়ি চলে যাই তাহলে মাইনেটা পার আওয়ার বেড়ে যায়।
শুরু হচ্ছে তো 20 মিনিট টাইম প্রথমটা না
May I have your attention, please? I kindly request everyone to take their seat so that we can begin the session. Good morning, everyone, and welcome back to day 2 of the conference. I hope you all had an insightful and engaging experience in the previous session. It is now time for the third technical session of our conference on dynamic processes of the Earth. This session focuses on experimentation and modeling of Earth and planetary processes, a critical area that combines theoretical frameworks, laboratory experiments, and computational model to unravel the complex mechanisms driving the planetary processes and surface processes. We are honored to have the session chaired by 2 distinguished experts in the field, Professor Sumit Chakraborty and Dr. J.K. Thompson. I would now like to request our esteemed chairs to kindly come onto the dais. I now invite our students to come forward and present flower bouquet to our session chairs. The keynote speaker for this session is Professor Sujoy Mukhopadhyay. The timing for the keynote presentation is 20 minutes, including questions and discussion. Following that, we will proceed with a series of presentations, each lasting 15 minutes with questions and discussion. With that, I now hand over the session to our esteemed chairs.
Hello, do you hear me? Yeah. So, welcome everybody to the session on experimentation and modeling of Earth and planetary sciences. And it's a pleasure to welcome all the speakers, and I think I'll just get started without much delay. So, it's a real pleasure to welcome Sujoy Mukhopadhyay from Arizona State University, and his talk will be on Earth's accretion and early evolution from xenon and fluxusion isotopes. Sujoy, please.
Point here, you have to look back there. Okay? DPE start. Okay. Will it be fine? This one is good. Which one? And the red switch is for pointer, this is for slide. Okay. DPE चालिए
Well, thank you to the organizers for allowing me the opportunity to talk. So it's a privilege to give the keynote presentation in honor of Dr. Shah. Almost 30 years ago when I was a student in Presidency, I never imagined that I would be here speaking in his honor. But thank you. So today I'll talk about xenon isotopes, and you will see that in the title I put tungsten in parentheses because the work that we have done involves both xenon and tungsten, but given the time constraints, I'll primarily focus just on the xenon. And this work had been done in collaboration with Professor Francis Nemo at University of Santa Cruz. So with that, let me just get into what the outline of the talk is going to be. So I'm going to first tell you about xenon isotopes, why they're useful, and why they're particularly helpful in looking at early Earth processes. I'll give you some observations that we have made in the past 10, 15 years on present-day sources in the mantle and what that can tell us about early Earth. And those observations are the motivation for the modeling work. Okay? And the modeling work is done to look at how we can explain the modern day composition of the mantle in terms of understanding when the moon formed, the rate at which the mantle was differentiating and partially melting early on, particularly in the Hadean. And I'll focus on three things in the modeling work. The first is the timing of the moon formation. So there is a fairly big debate about the timing of the moon formation. It's somewhere supposed to be 40 to up to 220 million years after the start of the solar system. If these later ages are correct, then that poses a problem for a lot of the dynamical models for formation of the moon, because it means you have to keep a lot of big bodies around in the solar system that late, and dynamically that's quite challenging. The next thing I'll do is, in context of the model, what can we learn about the distribution of volatiles after the formation of the moon, meaning how were these volatiles distributed between the interior of the planet and the surface of the planet or its atmosphere. And because xenon is a gas, it's particularly helpful in terms of tracing this process. And lastly, I'll focus on the Hadean mantle processing rates. So by processing rate, I mean the rate at which it is undergoing partial melting, Hadean magma generation rates, and crust formation rates. So the first introductory topic is the stable isotopes of xenon, and there's a lot. There are 9 stable isotopes of xenon. And 4 of these we call to be primordial, which means that they're not produced by any processes on Earth. The Earth inherits these isotopes, and that sets the abundance and isotopic compositions of these 4 isotopes. And then on top of that, we have another isotope. The Earth also inherits this isotope. It's xenon-129, but it's produced by radioactive decay of iodine-129. The importance of iodine-129 is that it was around in the early part of the solar system's history, but it's now extinct, and it becomes extinct after 100 million years. So again, this particular isotope is going to be present only for the first 100 million years of Earth's history. And then we have 4 additional isotopes, 131, 132, 134, 136, and these are produced by spontaneous fission. But they're produced by spontaneous fission of 2 separate isotopes, plutonium-244, which is also an extinct radioisotope. So plutonium was alive for the first 500 million years of Earth's history, and it's produced by uranium, which is still alive. Now, plutonium and uranium produces these 4 isotopes in different proportions, which means that if I can measure these isotope ratios in rocks very precisely, I can figure out what fraction is coming from plutonium and what fraction is coming from uranium. And if I have a reservoir that has undergone very little degassing, most of these isotopes will come from plutonium. If I have a reservoir that has undergone extensive degassing, then most of that isotope is going to come from uranium. And the reason is that because plutonium is only alive for the first 500 million years, a lot of degassing after 500 million years will deplete all of these isotopes, and then the only available pathway for producing these isotopes is going to be uranium-238. And then if I have some kind of an intermediate degree of degassing, I'll have a mixture of these two. So one of the things to kind of notice in this talk is I've color-coded these isotopes, so any kind of plot you will see any isotope that will be colored in purple is going to be primordial, which means it has no pathway for production. And then here I am starting off the Earth with primordial isotopes of xenon. This includes all of the 9 isotopes. And then over time, I'm going to produce some isotopes from radiogenic and fission ingrowth. And so here are some examples. And again, in all of my slides, if you see a green colored isotope, that is going to be coming from iodine around for the first 100 million years. If it's going to be red, it's going to come from uranium. If it's going to be orange, it's going to come from plutonium. So I start with an initial set of xenon isotopes, and then I produce them through radiogenic ingrowth and through fission of plutonium and uranium. And then I lose some of these isotopes through degassing. So notice I'm going to just take out a chunk of these isotopes. And now depending on when I do my outgassing, I will keep replenishing some of these radiogenic isotopes. But if it is late, then I do not replenish any of my iodine-produced isotope, and I do not produce any of my plutonium-produced isotope. I will only replenish the uranium-produced isotope. So what this means is that the rate of degassing and the timing of degassing is going to affect the radiogenic isotope composition of these 9 isotopes. And so I've listed these 4 different components that are going to be present in the Earth's interior. And because we have lots of isotopes, we can uniquely determine what fraction of each of the isotopes are coming from primordial, what is iodine derived, and what comes from plutonium, and what comes from uranium. Okay. So here is another kind of schematic. This figure shows you time on the x-axis and the isotope ratio on the y-axis. So on the top, I have the iodine-produced xenon-129 against this primordial xenon isotopes. And again, remember, this is only alive for the first 100 million years. So if I have a differentiation event which fractionates iodine from xenon, I generate a reservoir that is degassed, and that'll have a high value compared to a reservoir that is undegassed or unprocessed. But after 100 million years, even if I have any additional differentiation or fractionation, I'm not going to change the ratio because the isotope is no longer alive, it's dead. So after 100 million years, the only thing I can do is I can potentially decrease this amplitude of variation between the 2 reservoirs by mixing them up. But I cannot increase the isotope ratios anymore. And in the bottom panel, I'm showing a long-lived system like either plutonium or uranium. And for uranium, for example, I can have uranium-xenon fractionation, and that uranium-xenon fractionation could have happened a few 100 million years ago. And so it has the ability to keep producing these more radiogenic values compared to something that is unprocessed or less processed. So the bottom line is that I have an element with 9 isotopes that has multiple pathways of production, some very early on, some that are ongoing. And because I can measure all of these 9 isotopes, I have a tool that basically tracks the entire history of the Earth in very high resolution. So extinct radionuclides are really powerful at looking at early events because of this ability to figure out what was happening in the first 100 million years, because I have a lot of resolution. So one schematic way of thinking about this is if I'm just looking at accretion, I would look at the iodine-xenon ratio. If I'm looking at the accretion and the Hadean, I will look at iodine-plutonium-xenon ratios. And if I'm looking at processes that are going from the Hadean to the present, I will look at plutonium, uranium, xenon because of the timing constraint. So again, 100 million years, 500 million years, and then this plutonium-uranium xenon system is sensitive to modern times. So with that, let's look at just one key aspect of the difference in what we consider the mid-ocean ridge basalt source and the plume source in terms of these xenon compositions, and what that can tell us about the Earth's interior. So here is a figure on the y-axis shows again the iodine-produced xenon against this primordial xenon. So again, green color is iodine, purple is primordial, and on the x-axis is the helium-xenon ratio. So these are some of the measurements we had done in our lab. So this is showing where mid-ocean ridges plot. This is showing where some mantle plumes plot. And so the basic point is you can see that there is a difference in this iodine-produced xenon isotope ratios. The helium-xenon ratio doesn't change that much. But this has a much higher xenon 129 over xenon 130 compared to the plume sources. So for a very long time, the argument was that this difference comes about through subduction of atmosphere. So the atmosphere plots down here. What you notice is, again, that the atmosphere has a lower value than both plumes and morbs. So obviously, you can kind of imagine that if you take this lower 129 value and you put it into the morb source by subducting air, you can pull this value down. But here is the critical point. When I make a plot like this, a mixing between two different components like morb and air is going to be linear. So that means that if I subduct air into the morb source, I can only evolve along this line. If I subduct air into the plume source, I can only evolve along this line, which means that I can't go in this direction through subduction of air. So the only possible interpretation that is left is that this has to reflect a iodine decay signal, that this is some difference in the xenon 129 produced from iodine 129, which right away tells us that the difference in the plumes and the mid-ocean ridge basalt sources were created sometime during Earth's accretion. And so that's going to be the framework in which we will do our modeling. And so here is going to be the observational summary. So what we see is for plumes, and I'm not going to really talk about tungsten today, plume sources have slightly lower tungsten isotope ratios than morb sources, and plume sources have lower iodine to plutonium produced xenon, and they have a much higher proportion of plutonium produced xenon compared to uranium produced xenon. When we look at morb sources, they have a higher iodine to plutonium produced xenon, and their plutonium to uranium produced xenon is much lower. So right away this says that this morb source has been degassed more, so it has lost more of the plutonium produced xenon, and it has been replenished by uranium. And so here is again our cartoon framework where 80% of our mantle we are taking as the mid-ocean ridge basalt source, which is partially melting to produce the oceanic crust, and then the bottom part is the plume source. So talking now about the modeling results, we are going to use a very simplified model. It has got 4 stages. In the very first stage, the Earth is accreting through small bodies. It is differentiating into a core and a mantle. And during this process, xenon is being lost from the mantle to the atmosphere. We are not going to track the atmosphere for the problem. And then part of the iodine might be sequestering in the core because iodine can get siderophile. And then in the second stage, we have a giant impact where something about the size of Mars collides with the Earth that generates a global magma ocean, homogenizing most of the planet. Again, during this process, there is going to be loss of xenon. The third stage is delivery of more volatile rich impactors. And we know that we need these kinds of delivery to account, for example, for the siderophile elements that we see in the Earth, such as palladium and iridium, ruthenium, and so on, because we know that to account for the abundances of those elements, we need these late accreting material. In the context of our model, what we will assume is that those small impactors only get added to the morb source. And then once the accretion is over, we switch over to a more plate tectonic style process where the mantle loses xenon by partial melting. So in the context of the model, we don't really talk about it as plate tectonics, but you should know that this is partially melting as opposed to having a global magma ocean. So there are lots of free parameters, such as how much xenon is being lost in each of these stages, what is the degree of equilibration between the metal and the silicate, what is the rate at which the planet is growing, when the formation of the moon is happening, and what we are trying to do is kind of solve or constrain some of these parameters given the modern day observations that I have summarized. So there is a set of couple differential equations that we solve. I'm not going to show that. Instead, we can just look at some examples. So this is an example of the accretion history that we look at. So on the x-axis is time in million years, and this is the mass fraction. And so this accounts for a range of growths. And in all of these, you'll notice kind of a vertical step. And those vertical steps are basically the giant impact that leads to the formation of the moon. And so what we are trying to do is to constrain the latest time period that would still fit the modern day observations with respect to these giant impacts. So I'm going to show one example realization of these models. So we are looking at the iodine to plutonium produced xenon, and the top is the morph source and the bottom is the plume source. And these shaded regions are basically the compositions of the modern day mantles for the morph and for the plume. And so here what you see is a giant impact that happens at sometime around 75 million years. And after that, Earth is still accreting, and then it switches over to this plate tectonic style outgassing. Now, one of the things you notice is that this particular ratio only evolves for the first 500 million years. After that, it is basically flat, meaning we are not sensitive to what has been happening with this particular system in the past 4 billion years, but we are very sensitive to what is happening in the first 500 million years. And so that's kind of what I'm going to focus on, is the first 500 million years. So the first result in terms of when the moon could have formed. So here is, on the x-axis, the timing of the last giant impact, and on the y-axis is the number of successful simulations that we can get. So remember, we are looking for a whole range of parameters in terms of how much iodine the Earth is accreting with, when the moon is forming, metal silicate equilibration, how much xenon is being lost. And one of the things you notice is that as the timing of the last giant impact becomes later and later, our successful scenarios drop, such that after 90 million years, we find no successful scenarios, which basically constrains the formation of the moon to a time period prior to 90 million years. That it's basically prohibiting any moon formation after 90 million years, and still able to match the modern day observations of the plume and the morph sources. And as I said, I'm not going to talk about the tungsten, but the tungsten basically constrains this last giant impact to no earlier than 40 million years. So what we are basically doing is putting a bound that this is happening sometime between 40 and sometime between 90 million years. And in terms of looking at the overall successful scenarios, it turns out that the most likely range is somewhere between 50 and 80 million years after the start of the solar system. And again, this was kind of, we thought, a powerful approach because we didn't actually pick any particular values. We were allowing for a whole range of parameter space search and saying, when are we violating, or under what conditions are we not able to fit the modern day observations? And the answer is anything after 90 million years doesn't fit modern day observations. And anything prior to 40 million years doesn't fit modern day observations. So the next topic is the volatile distribution following the last giant impact. So again, this is the timing of the last giant impact, and this is the fraction of the radiogenic xenon. So this is the xenon that is produced within the Earth. And what you notice is that at most, we get something like 5% of the gas retained in the interior. Now, we do not outgas xenon on its own. Xenon goes to the atmosphere carried in bubbles like CO2 and water. And so under all scenarios, we are seeing at most 5% of all of the volatiles that could have been in the interior remained in the interior following the formation of the moon, which means 95% was on the surface. If you look at the modern day world, things like carbon, 90% of the carbon is actually in the interior. So that must be a history following the formation of Earth's accretion or following the formation of the moon. And then lastly, I'm going to talk about the processing rates only in the Hadean, the first 500 million years. So these are example scenarios that fit, again, the modern day observations, and what we are seeing are processing rates being 7 to 10 times higher by the time the Hadean ends. So processing rates are, again, the degree of mantle that is partially melting. And the next figure shows you the timing of the giant impact and the fraction of the mantle processed by the end of the Hadean. So even for the 85-90 million year last giant impact, we find that by the end of the Hadean, at least 60% of the mantle has now been processed by partial melting and therefore has lost its volatiles. So what does this number really mean in terms of so much mantle being processed? So this is enough to produce almost all of the modern day continental crust. Here is an example. So there are uncertainties as to what the degree of partial melting is. We assumed it to be between 20% and 10%, and we took an oceanic crust that is somewhere between 10 kilometers and 20 kilometers thick. So what this would mean is that by the end of the Hadean, you would have produced at least enough oceanic crust to resurface the whole Earth at least 10 times and maybe as much as 30 times. So this is a voluminous amount of magma production that is going on by the end of the Hadean. And so with that, I'm going to conclude that the moon formation was prohibited after 90 million years, and most likely it happened prior to 85. That at least 60% of the Hadean mantle had seen partial melt extraction by the end of the Hadean. And this is enough magma generation to resurface the whole planet with oceanic crust at least 10 times. And that enough mantle is being processed and enough magma is being generated to produce the entire mass of the continental crust by the end of the Hadean. So thank you.
Thank you, Sridhar. Thank you particularly for giving an excellent introduction to xenon isotopes. I think that's very helpful for the students and everybody else with a question. We'll take one quick question. So, during the degassing, you assume no fractionation of the isotopes takes place?
Yes, during degassing, we're assuming there is no fractionation of isotopes. And the rationale for that is that because we are looking at isotopes that are produced by radiogenic decay, any kind of delta level fractionation that might have been produced by the degassing itself would be quite small compared to the overall signal that we are looking at.
It's much smaller than that.
It's much smaller, yeah.
That's useful.
Yeah.
Thank you.
I have one question. Yeah, can the same analysis be performed on shocked minerals?
Sorry, can you?
Shocked minerals.
Can the analysis be done on shocked minerals? So yes, you can do the analysis on the shocked minerals, but you have to know something about the history of the material that is shocked to then kind of interpret what you are looking at. So for example, you can start looking at shocked material from the moon, but you have to know like when that shock event happened to understand something about whether that shock might have reset some of the isotopes and then replenished some other isotopes. But in terms of the measurements, yeah, certainly they can be measured in shocked material. Yeah.
Thank you. Okay.
Thank you.
Thank you, Professor Sujay. Moving on, now we'll be having our session talks. We'll start with Dr. Arindam Datta from GSA Kolkata. So Dr. Arindam will be talking on correlation of Raman spectral parameter and mineral phase chemistry from ordinary chondrites. So I welcome Dr. Arindam to deliver the talk.
I want to use a pointer. This is the for changing button and this is for point করার জন্য যদি আমার মনে হয় ওদিকে তাকাবেনই না বেটার এটা তো আমি এই পয়েন্টারটা অন করে দেবো আপনি এখানে করে সব কিছু করে দেবেন বেটার
Thank you. So may I start, sir? No. So good morning to all of you, and I just thank the organizer, especially Professor Shankar Bose, because I came very late. We know about this conference very late, but still he's accepting our abstract. Thank you for that, sir. So this particular topic is our standard GSI FSP program. It was done by me, my colleagues, Dr. Kosik Chakraborty, Aninda Bhattacharya. So what we actually try to do here, basically the objective, if you see, we have some of the chondrites of our GSI own collection. So we have taken some of the samples and we try to correlate this, their XMG, the mole fraction of olivine for this, pyroxene also, orthopyroxene especially, and to correlate them, their Raman spectral parameter, whether they can be fitted and this can be applicable to our normal terrestrial rock of their same equivalency. So on that note, we take this item, it's an experimental project of from our GSI end. And now, before we go to the details of what we have done or what we have got, so basically this we have selected the chondrites of varied chemical and petrological types of different, and they all are ordinary chondrite. As you know, ordinary chondrite basically of H, L, and LL type of their chemical constants. So this particular gamut of samples, if you see their distributions, so basically they have these 10 samples we have selected of H, L, or LL, they are of different chemical, and the followed the number is given 5, 6, or 4, these are the petrological types. So basically the ordinary chondrite, if I just go back, this is the sample, you can see this is the chondrule, this is the very tiny chondrule, this is their building block of these particular samples. And by mineralogy, if you see the mineralogy of this particular suite of samples, they are basically composed of olivine, orthopyroxene, sodium diazoxide mostly albite, clinopyroxene, apatite, merilite, and a few opaque phases. They are including your magnetite, trollite, chromite, and some of the iron, nickel metals basically, either camacite or titanite. So basically, these are the very common mineralogy for this group of the chondrites. And if you see this mineralogy, so if we correlate them with our terrestrial counterpart, so they can be broadly fitted with the mineralogy component with your peridiotites or the pyroxenates, basically the lower to upper mantle clinop rocks. So these are mostly the gabbro, the olivine basalts, or the picatic basalt, the dunite maybe. So by mineralogy, they are very close by them. You can be approximating them. So for this study, we choose this suite of the chondrites of different chemical and petrological types. Along with them, we also take some of the samples of the crustal, the lower mantle rocks of different tectonic setups, and we try to correlate whether the XMG we are calculating from this chondrite and from these terrestrial rocks, how far and how best they can be fitted with the XMG and their Raman spectral parameter, particularly for olivine and orthopyroxene. But if you see the texture of the chondrite, those have been very, well known in the study, the texture is completely different from the terrestrial rocks. This is the chondrules, these are called the chondrules. This is from the Bishnupur chondrites. So chondrules are very much conspicuous here. So for this study, we choose the samples for the chondrites. There are several types of, the chondrules. It's called the radial pyroxene, barred olivine, porphyritic olivine, porphyritic pyroxene, granular olivine. It's a textural composite grain. So we try to estimate the XMG of the olivine and pyroxene through the EPMA of these different textural phases. And we try to corroborate the same, the minerals, same phase, mineral phase with their Raman spectral parameter at GSI only. So same sample, same grain of olivine or orthopyroxene of different textural affinity, we take their XMG in note, and same grain we try to have their Raman spectral analysis through the Raman spectroscopy study. But there are certain constants. The constant is that sometimes chondrules are really big ones. And in the EPMA, we have a very better resolutions in the BSC or BSC images. those are lacking in the Raman. So the phase we're analyzing in the EPMA, those are the phase of different chemical, there's a variation in the chemistry in the XMG content. So sometimes we are not able to pinpointing those points in the Raman, but we try our best. We try to fix those locales where this EPMA has been done. From the same sample, we try to get the Raman spectral parameter of the olivine and the orthopyroxene for the study. Now, there are certain constants also. Say, if you see this petrographical evidences from the chain which is LL3, then Mirzapur which is L5, and the Bori which is L6, from L3 to L5 to L6, there's a certain change in the condole distributions. As the petrological types increases, the condole size and shape, they are generally vanishes. If you see from chain put samples, the condoles are very much conspicuous. But gradually in the Mirzapur L5 and L6 in the Bori, the condoles are almost diminishing with the matrix. And moreover, these two samples are shocked also. Shock means they have been undergone some shock metamorphism. Shock metamorphism also can control the change of the mineral phases from the olivine, orthopyroxene. They might have been transferred to the high pressure polymer also. So this constant we have to take into consideration while we are calculating their XMG and their Raman spectral parameter. So whether these minerals are shocked or unshocked, this has to be taken into consideration prior for their analysis also. So with this constant, we gradually go forward for the olivine first. So as you know, olivine has around 36 vibrational modes in the Raman spectral parameters. So it's not possible to take all into the account. So we take this, we call this the Fermi doublet. This is the 856 and 820 are the two most prominent peaks for the olivine. We take into consideration them, and their difference is known as the omega, which is the 36 centimeter inverse for these particular minerals. And apart from that, we also take two another auxiliary peaks. One is the 920 and 966. We'll come to this account also. So general trend for this Conrad samples, which are the equilibrated one. So we gradually see, we calculate their XMG and the peak shifts. So we can see that there's an increase of this omega value, this value of difference of their two prominent peaks, the Fermi doublet peak 820 and 856. This peak shift is gradually increasing with the increase in the XMG for the olivine, for the chondrites. Now, apart from the chondrites, the terrestrial counterparts which we take into consideration from different tectonic setup, like from the marble from Meghalaya, then from your different basalts of Saurashtra, ophiolates from Andaman, then from your some of the high Mg olivine from the Turkala complex. So different techniques that we take into consideration. We gradually take their Raman spectral parameters and the XMG in correlations. Now we take into account these olivine grains for these meteorites of our own choice, own list, and this terrestrial sample, and we try to corroborate them with the already published results of your Wang et al. 2004, and Moore and Enemy 2008. They have used the same setup, the same chondrite of differentiated chondrite and undifferentiated chondrites and other samples also to calibrate how far, how best this can be used in the space mission. So now for our study, for the rock we have selected and the chondrite samples. So this is for your that 820 peak for the olivine. So we plot the XMG and we plot the XMG against the 856 of the olivine, and we found there's a well correlation from the chondrite samples as well as the terrestrial samples of our this normal lower to upper mantle rocks. And again for the 915 and 966, the two secondary auxiliary peak for the olivine, we take the same account for our own sample from the chondrite and from the terrestrial sample, and we found that the correlation is quite good for both the peaks. So for olivine, all the peaks, the correlation of this XMG and that Raman spectral parameter are well correlated. Now, if I plot them, if I correlate this our own data set with the two data of the Modi enemy of 2008 and Wang et al. 2004. So this is for the blue for that your Wang and red for your Modi enemy. So if I plot them, so there's some control we have when we compare our own data with these published plots. The question is that if the XMG value for the olivine is more than 0.5, if you see the more than 0.5, So these blue lines, the blue lines are oil fitted. The results of the Mori enemy are oil fitted. But it's below 0.5, then it's deviates that it's the blue lines, I mean that Mori enemy lines, the red lines, they are quite deviated from our own results. So there is a marking of 0.5. If it is more than 0.5, the results of the XMG from our calculated samples, so it fitted well for this model. If it is less than 0.5, so it is bit deviated from our, I mean the published results, and it's not been well calibrated with the results of the Morian enemy. This is the one constant of the 0.5 for the olivine. Secondly, for the Wang, so we calculate our results and we plot them for these plots of our own XMG value. This is the plots from the Wang et al. 2004. We plot our data. So it's come around the 0.6. If your XMG is more than 0.6, so it is somewhat, it's well fitted or well calibrated with the published results of the Wang et al. It is below 0.6, so somewhere it get deviated from our own, I mean that results we have from this published data of the Wang et al. So 0.5 to 0.6 is our control for the XMG for the olivine, which suggests that after these values there is some deviation for the olivine to being calibrated well with the published results for the particular for normal terrestrial rocks as well as your chondritic samples. Now for the orthopyroxene, the case is a bit different. Orthopyroxene have different vibrational mode. So we take into consideration of these four bands. One is the 334, then one is the 665, 687, and last one is the 1014. So depending on that, we calculate the same procedure, the same mineral, we calculate their XMG from the EPMA and Raman from the different peaks, different vibrational mode, and we try to plot them. For the orthopyroxene, the data are not as calibrated as the olivine. They are bit, I mean, disoriented or not fitting in the linear equation. So this is the one case they are fitting in the linear equation, but most of the cases, the values of the XMG gradually decreases when they are Raman peak spectral values. They are also decreases. From one point to another point with the decreasing trend. So they are mostly fitted in the lines. I mean, not in the lines, either in the parabolic equation or bit scattered in your binary plot. So for this orthopyroxene grains, so if you plot them in one of the model of the Wang, so this is the graph given by the Wang, the red one. So our data is plotting either beyond the graph, either on this side or that side. So data from the orthopyroxene are not as well calibrated as compared to the olivine for the chondrite sample as well as from your terrestrial rocks. So the data we obtain actually from the EPMA and what we got from this graph, if we fit them, so they are bit lowering estimation. So they are not fitting the estimation of what we observe for the olivine grains for both your chondrites as well as the terrestrial rocks. So the questions comes here. So whether we can hypothetically propose this our work or this type of experiment in an unmanned planetary space mission, where we can send us. So one more slide, sir. I have one more. Where we can send a space mission and they can estimate what is the composition by taking this account of their Raman spectral parameter. So there are certain constants, as you see that for the olivine, as I told you, this is a systematical variation in the peak position. It is generally increases with the increasing of their XMG values. For most of the peaks, 820, 856, 915, 1966. But for orthopyroxene, we have certain constant, because the constant is that we cannot have a linear equations here. We have either parabolic equation or the different scatter plot. So you can plot them together, or we can see the control is not very much obvious for the orthopyroxene grain when you compare with the terrestrial and the olivine samples. And the olivine samples. So with this note, so we have some precautions, we have some constraint to utilize this theory or this proposal or this, the experiment in using the unmanned space mission, where we can have the control that you can send your space mission and you can take your samples, scan them by the Raman spectral parameter and know whether what composition it could be with this constant. So with this, I have completed my part. So I'm happy if we have some questions from your end. Thank you. Thank you all.
Thank you. Thank you, Harinder. Can we ask a few questions?
So Arindam, it's an excellent talk. Just curious to know that your Raman shift versus XMG values of olivine, there are some values plotted in the very low XMG region.
Yes, sir.
2 or 3 plots.
This one, I think. So these are the, I think not the chondrite, this is the terrestrial, some of the terrestrial rocks. They are the phyletic, I hope these are the, this one, sir. Phyllate bearing chondrite from the Turkella.
And now in the other plot.
This plot, this one.
It's to left-hand side, left-hand corner.
These two.
Yeah.
These are not, sir, I mean, these are phyletic olivine, not the phosphatic olivine. That's why they are, these are not the chondrite sample, they are terrestrial sample, sir. Terrestrial sample.
Thank you.
I have a question. So, first of all, if you have your microprobe data, why are you relying on Wang et al. or the other study?
No, sir. Actually, sir, they have done for the both differentiated and undifferentiated gland. We are only dealing with the undifferentiated rocks, the chondrite part. So that's why we have to compare how the results we have, whether they are matching with them or not, just for a check.
But I think on the mineral, it's the mineral that controls the spectra, right? So if you're measuring your own mineral with a microprobe, that's much more robust than any general correlation that they may have had.
Now, we can measure directly, no issue. We are proposing that if we get some samples, which is the unknown samples, we only have the Raman scan of the peak. Whether from the Raman scan, we are able to know what the composition it could have based on the XMG. That's our proposal for the space.
You can try to develop your own calibration is what I'm saying.
Yeah. That can be done. That can be definitely done. But we are checking our results with them because they're the published results. So we try to do that.
It's a good first. Yeah.
Thank you, sir. And lastly, I have seen one more slide. So GSI has a repository. It's a new repository, newly launched. It's a very good one. So I request all of you to please come forward to our GSI headquarters building in Kolkata and come and visit this repository of GSI collections. Thank you all.
Thank you, Dr. Thompson. We move on to the next talk by Bappa Mukherjee from WIG Dehradun, Machine Learning Assisted Crustal Velocity Proxy in Northwestern Himalaya.
এখানে সমস্ত সিস্টেম করতে হবে অথবা
অন আছে
either this or if you can choose this one.
ঠিক আছে পেনটা থাকুক ওখানে
এটা দিয়ে পয়েন্টার এই দুটো দিয়ে চেঞ্জ হবে ঠিক আছে
এটা তো পয়েন্টার না So good morning everyone. Myself Bappa Mukherjee, currently serving as a scientist B at Wardian Institute of Himalayan Geology. So first of all, I am thankful to the organizers for giving me the opportunity to deliver a talk in this platform. And so today I am going to talk on machine learning assisted crustal velocity proxy in Northwest Himalaya. So let us understand the problem and its importance through a graphical outline. So generally, if someone want to assess the crustal velocity movement, then one has to establish the permanent mode or campaign mode GPS stations. And it costs around, for permanent station, it is around 30 lakhs, and for the campaign mode, it's around 15 to 16 lakhs. So the question arises, can we predict or assess the crustal velocity from the existing GPS stations? So through the machine learning, the question is yes. And the answer is yes, we can able to assess the crustal velocity based on the existing GPS networks. So come to the material method section. Now suppose we have the GPS stations, maybe this is permanent mode or campaign mode. So from these existing stations, first we have to consider few stations
as a training station and few stations as a test station. Here the training stations are colored in the red color and the test stations are marked in the yellow colors. So in GPS basically we have the location, that is meant latitude, longitude, and in GPS we have two kind of velocity, that is easting velocity or northing velocity. So here in that particular case study I have utilized support vector machine, Gaussian Poisson regression and artificial neural networks. These are the three machine learning approaches. So our objective of the study, so these are the already available existing networks and we want the velocity at our desired location. This is marked in the green color. So through the machine learning models, we have to feed the latitude and longitude as the input and the velocity, that is easting velocity or northing velocity, as output. And then we have to train the models, and then after that we have to feed the latitude, longitude only, mean the position of the test networks to test our machine learning models, and then once we get the satisfactory level of accuracy during training and testing, then we have to feed the desired location, that is virtual location, virtual GPS stations, and then we can predict the velocity at the virtual locations. So now move towards the case study. So in that case study, I choose the location, basically the Northwest Indian Himalayan region. And Northwest Indian Himalayan region basically contains 4 Indian states. These are Ladakh, Jammu Kashmir, Himachal Pradesh, and Uttarakhand. So this is basically our available data sets. That is data courtesy from the Jiang et al. And we are having total 1,271 data sets in this study area over the Tibetan Plateau and its surroundings. So in that case, to train the model, we have chosen this area, basically marked by the red color GPS stations. So these are 920 in number, and to test our models, we have chosen this area, mainly located in the Indian Himalayan region and upper part. So these are having 351 stations. So approximately 70-30 ratio, we have segregated our total data sets. So now we have to now it's time to implement the machine learning algorithms. So with this 920 stations means data, means GPS velocity and their locations, we have to feed the data into the machine learning models. So as I earlier told that in this case we have used support vector machine, Gaussian Poisson regression, artificial neural networks. These are the 3 machine learning algorithms I have applied, and these are the network architecture with the latitude and longitude. This is the position mainly feed as the input, and we designed 2 different networks to predict the easting velocity and northing velocity. So after train the model, here we have total 920 data set in a single channel. So nowadays in modern machine learning, in earlier days we generally to train the model, we have to generally people segregate the data into 70-30 or 80-20 or 90-10 ratio. But nowadays we generally use k-fold cross validation. Here the entire training data set has to be divided by a number, means here total 9 groups, and each of the groups having more or less same data sets, and using the leave one out model. Suppose this particular case, this is the validation set, and the rest of the data used for the training. So here I have taken the value of k is 9, so entire data sets is segregated into 9 groups.